Question 3, we're looking at magnetic fields. For this question we have this constant here, okay, that's from the formula B equals Ki over D. So that's a formula that's going to come up later, so that's what that's related to. A constant current is passing through a straight wire in the downward direction. A magnetic compass is placed near the wire as shown on the diagram below. Part 1. On the diagram, draw an arrow to show the direction of the magnetic needle inside the compass. Okay, this uses the right hand rule to find, which is getting into part 2. We're explaining the right hand rule. Explain why you have drawn the arrow in the direction above. So remember, your thumb for the right hand rule gives the direction of the conventional current, and your fingers give the magnetic field, B. B is the symbol for magnetic field. So our thumb from our right hand, it's a right hand rule. Our thumb points downwards in the direction of the conventional current, 20 amps, and our fingers curl around that way. So that shows this direction around, that's supposed to be joined around there. So that means in this loop here, it's going to be pointing roughly in that direction. Because it's, roughly speaking, out in this direction. It's a 3D drawing, so it's a little bit tricky to get, but the circle will be passing around in front and behind at the back there. Okay, in the direction that I drew. So that answers the reason why it's the right hand rule, and that's the direction of the arrow. So if we're explaining why, we would just explain how we applied the right hand rule, maybe even detailing out thumb and current and fingers and the magnetic field, and how that works. B. Calculate the strength of the magnetic field is 0.14 meters away from the wire due to the constant current. Remember, the current was 20 amps. So that's two pieces of information. We were also given the constant K at the top, and the formula that links those is B equals Ki over D. When you put those numbers into the equation there and calculate it, you find the magnetic field comes out at 2.9 times 10 to the -5, and the units are teslas, T or T4 teslas, which is the unit for magnetic field. It's a strange one because we're not used to it, but it's still fine. C. An identical wire carrying a constant current of 20 amps, same 20 amps again, but we've got it in both of these wires, identical that is now placed near the existing wire. Current flows in the downward direction in both wires as shown in the diagram. The point P 0.14 meters away from each wire. So there's point P there, and it's equal distance from each wire. The real question here, well, that was just prepping you for it. The real question says, state the strength of the magnetic field at the point P and explain your answer. Now, the best way to approach this, because this is a state, it's not a calculate. We don't need to do any calculations. So the best thing to do is to use our right hand rule to check the field around both wires. So I'll have to do this in different colour because I've already drawn on the diagram with blue. So right hand rule down, thumb, and the magnetic field will then be passing around the front and back and behind in that direction. So it's that direction where they meet in the middle, and so forth. Same for the other one, around there, around the back, in that direction, in that direction, in that direction. So what we notice about this is we've got one going in that way and one going that way. So they're both going in opposite directions, and what we'll find is they will cancel out. Because of that, remember they're equal in value, equal current, and equal distance apart. So that means everything in our equation, B equals Ki over D, current's the same, distance is the same, K is the same, it doesn't change, it's a constant, so the magnetic field strength is the same. So that means they're equal and opposite, which means they fully cancel out, meaning there is zero. If you're stating the strength, you would be stating zero magnetic field, or the magnetic field strength is 0 teslas. and the explanation is everything that I've left before them. Anything else? No, that's it. Good one, short one. Okay, there was actually another question. I'm just going to see if I've got it down. Oh, I do have it down here. There we go. It was just way off the bottom. This question is asking, we've got the diagram below showing the magnetic field of the Earth. And you can see the lines, magnetic field lines there. On the diagram above, use the letter W to mark two positions. So there's two places where this field is the weakest, and explain why you selected those positions. Well, we know that the magnetic field, the field lines, they show the strength. And where the lines are close together, so close, that equals strong, and where they're further apart, so wider spacing, that means the magnetic field is weak, or W in this case. So on the diagram above there, we can see these areas where it's very strong, and particularly around the north and the south poles. And these areas are where it is looking the most weak, maybe up a little bit up here and here as well, but those ones are sort of, I don't know, a little bit far out. It's a little bit hard to know exactly whether this question is looking at these ends, or whether it's looking at these parts here, but I would suggest it's probably looking here and here. That's why I'd put W. One, because the marking schedule says so, and two, because it's a bit vague at these endpoints. So I'd ignore them and stick with the clear and obvious ones. And when you give your reasons, you're talking about the field lines as the spacing. So now that's really the end of this question.